we could grab our seats, and we'll get ready for our next presentation. Dr. Glenn Kissel will be introducing our next student.
So thank you, Dr. Mitchell. I'm happy to introduce Mr. Eric McCord this afternoon. He's from Pike County, Indiana, and he took on the task of designing a subsystem for a project that we didn't know was going to take off or not, so to speak. So he really didn't have a team to work with, except John Sapirski was working on a mechanical prototype. And it was only toward the end of the semester that we finally found out that, yes, we're going to eventually build a CubeSat. So I appreciate Eric taking this on with kind of an act of faith, not knowing for sure what was going to happen. So thanks, Eric.
Okay, hello, and welcome to my presentation. My presentation is on designing a prototype processor CubeSat subsystem. So this is a little brief overview of what I'll be talking about today. First, I'll give you an introduction to CubeSat so you kind of know what I'm talking about. Then I'll go on to talk about USI-specific CubeSat, what's the same and what's different about other CubeSats. I'll give you the objective statement requirements for my personal project, not the USI as a whole, the USI project as a whole, but my project in specific. Then I'll give you some conceptual designs that I came up with and decided between for the final design of this subsystem. And then the parts and functions that I need for this project, the cost of each of these parts that I'll be using, how I tested my subsystem, and then finally some of the risks that I faced while testing this subsystem. So first, what is a CubeSat? A CubeSat is a miniature satellite that is typically designed for education purposes, so a lot of graduate students will design and build these CubeSats as a project. The first proposed CubeSat was in 2000, and the first one wasn't launched until 2003. But because they're so small, usually they're tasked with small tasks like data collection because they can't house a lot of equipment. And usually they're ferried to space by a larger rocket, so they don't have to have their own propulsion system to get into space. This pie chart kind of describes how CubeSats have went so far. As you can see, there are only 19.5% of all CubeSats have actually completely succeeded in their mission. That accounts for about 82 of a total of 421 CubeSats. There are 108 satellites in orbit now that can fall underneath the category of completing their project, but there's a lot of CubeSats that have failed or were lost early, so they didn't complete their mission. So this project is a very high risk, but it's also a very high reward. So this is kind of a CubeSat concept of operation, so kind of how a CubeSat operates as a whole, not my specific project, but the CubeSat as a whole. So first, the CubeSat is loaded onto a larger rocket, which will be used to carry it into space. So once the rocket is the proper distance, the CubeSat can be ejected from the rocket and into orbit around the Earth. And while it's orbiting Earth, it will complete its mission. And after its mission time is complete, the CubeSat will re-enter the Earth's atmosphere where it burns up. So USI's CubeSat specifically, this is actually the first CubeSat for USI, so it's kind of a big leap like Dr. Kissel said. We are modeling it a lot off of Taylor University's CubeSat. They actually successfully launched a CubeSat, so it's kind of nice to base it off of a success. And our design will be a 2U CubeSat, so what that means is it's going to be 10 by 10 by 20 centimeters, so it's very small. This is a representation of how large the 10 by 10 by 20 CubeSat will be. Our mission time is going to be roughly 30 to 60 days, where it's going to collect temperature and plasma probe readings. So this CubeSat is headed to the lower ionosphere, which is the upper mesosphere and lower thermosphere, and that's about 120 kilometers from the surface of the Earth. So that's kind of a general idea of where we want to send this CubeSat, and the reason for that is this section of space is a largely unstudied section, so we kind of want to take a little bit of data there and get some data collection from that unstudied part. This subsystem breakdown is kind of a breakdown of the general subsystems that all CubeSats have. There are more subsystems, but these are the most general. So we have an attitude sensing and simulation, a communications processor, a power system, a flight processor, the mechanical, and thermal. But for this senior design project, I will only be focusing on the flight processor. So this is the objective statement for my project specifically. My objective statement is to design, build, and test a prototype flight processor subsystem using components that will be implemented in the final CubeSat. So it's kind of a testing to see which parts are going to be a viable option to use in the final CubeSat that we send to space. So these are the shell requirements that I kind of set out for myself for this project to kind of follow those guidelines. First, the subsystem shall be powered by a battery pack, so it won't be plugged into the wall or into the computer or anything. It's going to be completely operated using a battery pack. The subsystem shall operate autonomously, so once you turn it on, it's going to operate by itself and you don't have to do anything else with it. And that's important for future use, because once it gets to space, you're not going to be able to do much except for send it signals from Earth. The subsystem shall use temperature sensors that we are planning to implement in the final design. That's important for this prototyping process because we're kind of just testing the parts. So it's important to use the final temperature sensors. And then the subsystem shall record and store the temperature data for evaluation. So for this flight processor, here are some of the parts that I'm going to be needing and kind of what they do. So first, we need a microcontroller or a processor. And this kind of operates as the brains of the system. It controls what other parts do and when they do it. So it's a very important part to the system. And that processor will be mounted on a platform, which acts as a central hub where all the parts can connect and communicate with each other. And then there's going to be like I said before in my requirements, there's going to be a battery pack that powers the system. And then there's going to be the temperature sensors that collect data, and that's going to be stored in the memory on the subsystem. So this is a general block diagram of what my system is going to look like. So you have the battery pack feeding into the platform, and you see the processor mounted there on the platform. And the platform will actually control what gets power, so the battery won't be directly connected to the temperature sensors. The temperature sensors will be connected to the platform, and then the platform will control how much power it receives. Now for this project, I have communications box there, but that's just as a visual to show you eventually it will use the communications processor, but that's not part of this project. So for the battery, I used a T-Energy Li-Poly 7.4 volt battery, and it's a lithium battery because they last a lot longer, roughly a year, and lithium batteries hold a better charge in cold temperatures, which it's going to be experiencing. So it was a little bit more expensive, but it's necessary for the cold temperatures that it's going to be subjected to. Next is the first of two temperature sensors I'm going to be talking about today. This is the AD590. It has a wide temperature range of negative 55 degrees Celsius to 150 degrees Celsius. It's a 2-lead temperature sensor, so one lead you attach a voltage to, and then the second lead will output a current that is proportional to the absolute temperature in microamps, which is a very small signal. Microamps is 1 times 10 to the negative 6 of an amp, so it's a very small signal. And this temperature sensor is a transducer, which means it converts a physical phenomenon into an electrical signal. And so I had a lot of problems implementing this temperature sensor because it's such a small signal. So here's a circuit diagram of the signal conditioning that I conducted. So first, the temperature sensor, the 8590 here in the left, outputs a current. Most platforms and processors read a voltage. So to convert the current to a voltage, I added a resistor there because the voltage is equal to the current times the resistor. So by adding this resistor, I was able to change the current signal into a voltage that the board can read. Now the next problem is the signal is still very, very small. So in order to get past that, an operational amplifier was added. Now this increases the signal based on the 2 resistors in the bottom. And I won't get into the math, but based on the size of those 2 resistors is how much the signal is increased. But I ran into another problem because the 8590 and the 1K resistor here had a DC offset, and it was a very small DC offset, but after the amplifier was implemented, the DC offset also was increased. So to correct that, a high-pass filter was used. And this was used to bring the signal back down to 0, so it would correct the DC offset. And we did this before the amplification just for simplicity. And this is the first conceptual design I came up with. And this is based largely on Taylor University's design. And I did this before conducting a lot of research on my other microcontrollers. So I came up with this before I did a lot of the research. So they use the PIC 18F2620. Now that processor is a little bit smaller than the one we actually went with, but it does use the PSOC software, which I'm not exactly familiar with, so I kind of wanted to use something I had a little bit more familiarity with, and I could learn a little bit easier. And they also use the 8590 temperature sensors that I just spoke about briefly. So it's important to note that the processor that they did use does have flight heritage, so we know it operates in space. They launched it on their CubeSat in 2014, so it's important to know that this processor does work in space. So now that I've given the first conceptual design, I'm going to talk about how I actually conducted research to decide on a different microcontroller. So I came up with a list of requirements and criteria to decide on which microcontroller I wanted to use. So the requirements that I used were basically, it has to be able to operate in low temperatures, because if it doesn't, it's going to be useless. It's got to be compatible with the other components that I'm going to be using. And it has to fit inside the CubeSat frame, which I have here. Now some of the criteria, these are the things that it doesn't have to have, but I want it to have. So I want it to be as small as possible, that way it can fit in the CubeSat and not take up a lot of space, so there's plenty of room for other components. I want it to have a large memory bank so I can program to it without worry of filling up the memory, and it can collect a lot of data points and store it. I want there to be attainable software so I can actually learn this in the future. The CubeSat can continue to learn the software that this microcontroller uses, and I want it to be relatively cheap. So here's a list of some of the microcontrollers that I considered. There were more, but some of them didn't qualify past the requirements, so I didn't even bother putting them in this presentation. So here I have kind of compared these microcontrollers based on the program memory size. And as you can see, the ATmega 2560 has the largest program memory. And this is actually the microcontroller we decided to go with. And I, based on the program memory and other specifications like clock speed and input-output pins, I designed a decision matrix to decide on which microcontroller to use. And if you want to see that further, it's going to be detailed in my report. So the second temperature sensor was the TMP36. It has a little bit less of a range. It's only negative 40 degrees to negative 100 or positive 145 degrees Celsius. It sends an analog output voltage, so the board can actually read that without much signal conditioning. So it's actually a 3-lead instead of 2 leads. So one lead you input a voltage, another lead is the ground to allow flow, and then the third lead is the output signal that you can read with the board. So the reason I wanted to bring this up now is because I used the TMP36 in the conceptual designs that I came up with. This is the second conceptual design. It utilizes the ATmega 2560 that I told you about earlier with the decision matrix. It also utilizes the Arduino Mega that the ATmega can actually come pre-mounted on, so it's a lot easier to not have to attach that board to anything. And then it's going to use the 8590 and TMP36 temperature sensors. And this was to kind of compare and evaluate how each one did differently under each stress. And the software that the Arduino Mega uses is kind of a C and C++ with some Arduino-specific commands. So, like the previous processor, it's important to note that this processor does have flight heritage. It flew on the Black Brant 9, which is a suborbital sounding rocket, and it was kind of part of NASA's initiative to reach out and say that they could use publicly attainable parts on their rockets. So it's important to know that this one as well has flight heritage. So the third conceptual design is kind of a spin-off of the second. What I wanted to do was reduce the size. So instead of using the pre-mounted Arduino Mega board, I would use what is called the TQFP100 board. It's over there in the green. And I would mount the microcontroller onto that board, conserving about twice the space. And it would also use the 2 temperature sensors. And for the rest of the parts that the Arduino Mega needs to operate, they would be placed on perf board, which is kind of like a circuit, only you have to bond the parts to it, and you can wire it up however you need be. And that would be attached to the back of the TQFP board. So the final design that we actually went with was the second conceptual design. And I've kind of laid it out here with pictures of the actual parts that were used. As you can see, the battery feeds into the Arduino Mega, and the Arduino Mega communicates with the temperature sensors through a breadboard. So this is a rehash of the block diagram that I showed you earlier with a little bit more population of some of the names that we're going to be using. As you can see, the lithium battery feeds into the Arduino Mega through a male power connector because the battery I purchased didn't come with a connector that fits the Arduino Mega. And then the Arduino Mega sends power to the temperature sensors and receives the signals back. This is the budget for my project. As you can see, I have multiple parts listed in the quantity, and that's to account for testing or failure of parts. That way, if I did lose part of my system, I could still rebuild it and not come out empty-handed. I'm going to talk about that a little bit more during the testing of why I had multiple parts. And so the total cost of this project came out to be $1,360, but that's a little high because I included parts for the high altitude balloon test, because that was going to be one of the testing methods I used for my project. So to pay for that project, there were multiple things I did, one of which was apply for the Endeavor grant, which we got approval for on March 4th, which funded my personal project. And then the USI CubeSat team actually sent a proposal to the undergraduate student instrument program, which is what Dr. Kissel was talking about. It's allowed us to go forward with actually designing the entire CubeSat. We got approval for that on April 7th. Now, something important to note is that CubeSats get free rides into space, so you don't have to worry about paying for a ferry trip into space. Now, this is a list of the testing plans that I went through. Some of these worked out to my benefit, and some of them didn't work out as well as I'd hoped. First, I modeled the temperature sensor code. Then I did a duration test on the battery and the memory. Then I was going to use the high altitude balloon launch to test the data collection. And then a cold air test and a liquid nitrogen test. So I'm going to get into each one of these a little bit more. So to model the temperature sensor data, I used a Grove Shield, which is basically a brand of electronics. And I placed that on a personal Arduino Uno and used the Grove temperature sensor to kind of model some temperature sensor code to see if it would work out well for when I got my parts, because I hadn't received them yet. So I was able to use this to kind of get a head start on the coding. So it was very nice to go ahead and get a head start. The duration test, what I did was I plugged in one of the batteries into my subsystem to make sure it would last the duration of the high altitude balloon launch, which is roughly 2.5 to 3 hours. So I plugged it in for 5 hours and it collected 600 points of data, and the memory was not full and the battery did not die, so it was going to work for the high altitude balloon test. So now onto the high altitude balloon launch, which was actually unsuccessful. So this is kind of just a cartoon to show you what would have happened if it was successful. So first, the subsystem would have been loaded into a capsule attached to the high altitude balloon. And when the balloon is inflated, it would carry the capsule and the subsystem into the lower stratosphere, where it would experience very low temperatures. And so I could test the temperature sensors in a low climate. And then finally, the balloon would burst and the capsule would return to Earth. An attempt would be made to recover the capsule. Now, it's not always guaranteed that you can recover the capsule, so this is kind of why I wanted to have multiple parts. In case we couldn't recover the system, I still had something to work with. So the subsystem was actually placed inside this aluminum frame here that was designed by John Sapirski using machinery we have here on campus. So the subsystem actually was operational, it was working fine, but unfortunately, due to high wind speeds, the mission ended prematurely after 3 balloon losses. So to make up for not being able to do the high altitude balloon test, I actually had the opportunity to go to Crane Naval Base and conduct a cold air test. Now what we did here was we constructed a cavity or a frame out of rigid styrofoam and thermal foam and placed the subsystem in the cavity along with a calibrated temperature sensor, and then using a piece of machinery at Crane, we blew cold air into this cavity, getting the temperature inside down to negative 27 degrees Celsius, and that was about as low as we could get, which isn't as low as we would have hoped to get with the high altitude balloon test, but it's still a decent test since we didn't get to do that. And here you can see this is a curve of the temperatures as I decreased the temperature, and it might be a little hard to tell the difference, but there are 3 different lines there, and it might be good that you can't tell the difference because it means that they were very close together, which is a good thing to have. And there is some noise here. You can see the temperature sensors drop rapidly and then return back to the state it was. But so it's nice to see a nice curve where it gets down to about negative 27 degrees Celsius. Now, as a backup test, in case the Crane Naval Base didn't work out, I was going to use liquid nitrogen. So I fill up a tub with liquid nitrogen and place the subsystem above the liquid nitrogen next to a mercury temperature sensor. And this wouldn't get anywhere near even the negative 27 degrees Celsius that I achieved at Crane, but it was still something to test if everything else didn't work out. So just a kind of a backup plan. Now, some of the risks and failures I faced while testing my system were things that I was able to prevent, like loose wires and faulty parts. So I could, after testing the subsystem multiple times, I could find out, okay, well, we need to hold this wire down more, or we need to use a different part because this one doesn't work. So I was able to prevent those those failures, but some that I couldn't prevent was like some of the temperature sensors that get less accurate after a certain range of temperature has been breached. So I couldn't really help that, but it wasn't that big of a deal because it was just less accurate. So at this point, I would like to acknowledge some of the people that really helped me with my project. Obviously, Dr. Glenn Kissel was my advisor, and he provided a lot of feedback and gave me a lot of research to look into. Dr. Paul Cuban provided the probe temperature sensor and shield so I could model my coding for the subsystem. Dr. Arthur Klobowski and Bradley Kicklighter spent a lot of time helping me get the 8590 sensors to try and get them to work. Unfortunately, we weren't able to do that, but we did get pretty far on it. So they answered all my boring questions. Dr. Brandon Field was my contact for the liquid nitrogen test, so he was very helpful in saying if the crane doesn't work out, we have a backup plan for you. And then I would like to thank NSWC Crane for allowing me to come onto their base to test my subsystem.
All right, questions?
Great job. In one of your slides, you showed the signal conditioning, which uses an op amp, which requires a dual power supply, +5 and -5. Where do you intend on getting that -5 volts with a single battery?
Well, actually, I was using one of the power benches whenever I was doing the initial testing, but I did have smaller 9-volt batteries that I was going to use if we did get the testing to work before the launch of the balloon. We did have smaller batteries that we could use, but I didn't have those on here because we didn't actually get it to work with the power bench.
Okay, and then with regard to your battery life test, did you ever calculate or experimentally determine the power consumption of your system as it's running and collecting temperature data?
No, I did not. I let it run for 5 hours, and after that I unplugged it because I think the microcontroller started getting a little bit warm, so I wanted to turn it off before I blew anything out.
Thanks.
Other questions?
What's the lowest temperature that the CubeSat would experience in space?
After a little bit of research in the section that we are hoping to get to, I think some of the lowest is -100 degrees Celsius. And the 8590 temperature sensor has actually been tested in -100 degrees Celsius with no physical damage to the temperature sensor. It was less accurate, but it didn't receive any physical damage.
Do you know what the temperature ratings of the components on the Arduino Mega are?
The Arduino Mega gets down to -50, I believe.
So what about the other components? Are they better than commercial rated?
Well, the battery is lithium, so that does go down pretty low. And then I haven't checked on the operational amplifier or the capacitor and resistors used in that because I didn't actually get it to work here. So I didn't bother looking to see if it worked at cold temperatures.
Last question I got. You said you did testing with a Grove temperature sensor. Is that similar in operation to either of the other two temperature sensors you planned on using?
Slightly, mainly just the general idea of the code was helpful, but the Grove temperature sensor uses a thermistor and the other two temperature sensors don't, so it's slightly different. Some of the equations I had to use in the code were different from the 8590 and TMP36.
Good job.
Thank you.
Any other questions? All right, let's give him a hand.